Right, at last. So 25 past 2. Right, okay. Sketch each of the following graphs, labeling all intersections and asymptotes. So basically, what is the shape of a graph like that? It's hard to describe, isn't it? Have a go though.
So one that looks like that will be, so it will have.
I can't even see your monitor, so if you don't mind trying to describe it in words, yes.
Yeah, it will have two. It will be two different lines, well, not different lines, but it will be two lines which will be symmetrical through the line y equals x, and it will be it will like come down to the, from starting high on the y-axis close to the y on the, in this case I think on the left hand side of the y-axis, and it will come down and then curve close to the x-axis and then tend to the x-axis.
Right, I think you're talking about this one. Yeah?
No, the other side, the other two segments, the other two.
Or this one.
Yeah.
Ah, well, if you meant that, I think you meant this.
Oh, yeah.
Which,
No, actually, hold on. I know how that looks.
which is interesting, yeah?
Yeah, I did it. I did say that, but I didn't. But actually, it would look like it will basically be like tending to the x-axis in the negative, and then it will cross through a point on the y-axis and then keep going up.
Like that.
Yeah.
Right, and that's warmer, getting warmer now, but that's y equals 2 to the plus x.
Yeah.
And this point here would be what?
That point would be 2.
1. Because
yeah,
x
is 1,
is
isn't it?
0. And so you've got anything to the power of 0. Y equals anything at all to the power of x always crosses there. So y to the 5x, how would it differ from y to the 2? Sorry, y of 5 to the x, how would it differ from y to the of y equals 2? What did I say? Y of? Y equals 5 to the x will differ from y equals 2 to the x.
It will just be a steeper line.
Steeper, and therefore more like that.
Yeah.
So notice it will have the opposite effect on this side.
Yeah.
So that would be 5 to the x if that's 2 to the x.
Yeah.
Speaking. What about 2 to the minus x then?
2 to the minus x would be it would be basically mirrored, wouldn't it?
Yes.
In
which mirror line?
In the y-axis.
Yes, as will, by the way, going from any function to the same function of minus x. It'll always be a reflection in the y-axis, won't it?
Yeah.
Good. So what do we get? We get basically that. Woo. Yeah.
Yeah.
For that one. What about 5e to the x minus 1?
Okay, so 5e to the x. So
what about 5e to the x? What about e to the x? This is what you should do. Start from a basic and then start transforming it.
Yeah, well, e to the x would look like that very first line we drew.
That one?
Yeah.
Hopefully not the very first. Not like reciprocal.
No.
But this very first, I agree. Yeah. So just then, e to the x will look exactly like 2 to the x, won't it?
Yeah.
Good.
Exactly.
And this point will still be. Pardon me. This point there will still be
1.
1. So what about 5e to the x.
That will make it steeper.
Yes, and not only that, but it will mean that the y-intercept is
The y-intercept is 5 times higher. So 5.
5. If that's
Would it make it steeper as well?
5e to the x, and it will be steeper as well. Yes.
Yeah.
And therefore more like that than the other one. That's true.
And then minus.
Oh no, hang on. Will 5 make it steeper? Yes. Well, the whole thing. So if that was basically, if that's e to the x, 5e to the x is it's going to be scaled up by 5. The whole thing is 5 times higher.
Right. Okay.
If for 5e to the x. So every y value is going to be multiplied by 5.
Okay.
Including this one, including these ones as well. So does it make it steeper? Yes. Yes, you're quite right. It'll multiply the gradient by 5. Yeah.
And then minus 1 will take it down 1.
Yes. So we'll end up where?
With the all shifted down 1, so tending to minus 1. And it'll cross through the 4.
Cross at 4. Oh, and yes, you're right. Tending to minus 1. Yeah. Yeah, you're right. It's coming down through 4 and is crossing the x-axis and tending to minus 1. So let's try and draw that a bit better. What you're asking for is, I think, we'll draw that one first. And then this can be minus 1. Y equals minus 1.
Yeah.
That can be y equals 0. And that can be 4. And we just need to find out what this is really, because they've asked for all intersections and asymptotes.
So just set x equal to 0.
Yeah.
And you'd get
pardon, sorry. Set what equal to 0?
y equals 0. Yeah.
Y equal to 0. So we're
And
solving 5 e to the x minus 1 equals
0.
0. That's right.
Then you'd get 5e to the x equals 1.
Yeah. E to the x equals
a fifth.
a fifth. X equals
X equals log e to the 5th. Log e5. Log e 1/5.
yes, or natural log of a fifth.
Yeah.
Which, by the way, equals how many of log 5?
Wait, I'm not sure.
Minus 1 of them.
Wait, so ln, I thought that was when you'd have 2 different values. Or is that log?
No. It means log to base e, which is what I thought you were saying.
Then what one is log to base 10?
That's what log means without any further indication, so by default. Log of 100 means log base 10 of 100, which of course is?
Which would be 2.
2. Power we have to raise 10 to get 100 is 2.
Mm.
So natural log means the power you have to raise e to get whatever.
Right, okay.
So, for example, if x equals the power you have to raise e to get a fifth, then x is that power of e, which gets you a fifth.
Right, okay.
So you can see why it is the negative of the power which gets you 5. Because if that's true, then that will be true, won't it?
E to the minus x. Yeah. Yeah, okay, yeah.
That would follow from that. Because that equals 5 to the minus 1. So if e to the x equals 5 to the minus 1, it follows that e to the minus x must be 5 to the plus 1.
Right, okay.
There is one other way of looking at it. There's so many different views of the same thing with logs and powers, and it's worth using them. Okay, so that's all in aid of just confirming, that this point here is minus ln 5.
Yeah.
Is the x value which turns y into 0.
Right, okay.
And then y equals log x.
Y equals log x. Okay, so that's what you have to raise 10 to get x.
Yes. Now, in general, I mean, what you have to raise e to get x, you mean?
Yeah.
So it's the inverse of e to the x. If you swap these around, if you swap x and y around and say x equals e to the y, and then you make y the subject, y is the power you have to raise e to get x. So the point is that the graph of y equals log x is going to be the inverse of y equals e to the x.
Right, okay.
Now, if I just move these down a bit into their proper, more helpful location. So they want y to the log x, and we've just noticed that it's the inverse of y equals e to the x. So,
yeah,
by the way, log base 10 of x would be the inverse of 10 to the x.
the inverse.
Yeah. Log base 10 of x is the power you have to raise 10 to get x.
Yeah. Okay.
So y being the power you have to raise 10 to get x is another way of saying that if you raise 10 to that power, you get x.
Yeah.
And if we swap that round and write it like that, we've got y equals 10 to the x. If we swap x and y around, which is what we're doing with an inverse, isn't it?
Wait, how can 10 to the x equal y if y equals log 10 to the x?
If we're doing the inverse of 10 to the y equals x, then we're swapping x and y around, aren't we?
Yeah, I just don't understand how though that could equal that.
Sorry, going from here to here?
Going from there to the bottom.
No, they're not equal. We're taking the inverse and therefore swapping x and y around. What we're doing there is taking the inverse.
10 to the y equals x, 10 to the x.
Do you see how 10 to the power of y equals x would be the inverse of 10 to the power of x equals y? Because we've just swapped the x and y around.
Yeah.
So we're doing precisely the opposite.
Okay.
To get
Right.
from x to y here, what we're doing is finding the power you have to raise 10 to get x. And then we're getting the power you have to raise 10 to get x. But if we go back again, we're going to be raising 10 to the power of y, and then we'll have x, won't we?
Yeah.
It's mind-bending. So you need to find ways of, you know, writing and drawing appropriate things to get your mind around it.
Yeah.
Saying it's mind-bending and, and saying let's leave it for now is something I found myself doing, and it's inadequate. we should get our minds around it somehow or other. And in the process of doing that, I'm probably rushing on occasion.
So you think 10 to the y would equal x?
Well, sorry. Yeah. Well, getting back from y to x is a matter of raising 10 to the power of y. Yes, if getting from x to y was a matter of finding the power we had to raise 10 to get y.
Right. Okay.
I lost myself then. I didn't follow what I just said. so make sure it's true. Let's say y is the power we have to raise 10 to get x. That's right. We're finding the power that we have to raise 10 to get x. We're putting x into here.
Yeah.
And we're getting y, which is log base 10 of x.
Yeah.
Then yes, this would be
10 to the y would equal x. Okay. Yeah. Yeah, I understand that. Yeah.
What is the graph of what's that the graph of, probably?
Y equals e to the x.
Yes. In which case, how shall I draw the graph of y equals natural log of x?
That would be y equals. So that would be, what are you raising? So that would mean e to the x. So no, that would mean e to the y gives you x. Isn't that just the same thing?
Yes. Yes. This is the graph of e to the y equals x.
Yeah.
Right. Well, how
Yeah.
shall we do, what would the graph of e to the y equals x look like? If the graph of y equals e to the x looks like that. What's the relationship between these two?
Inverse.
Inverse. And of course, which is why these are the inverse of each other. That's a
Yeah.
version of that. So you can see directly why these are the inverse of each other. Now, we're trying to draw the graph of this, or this, this, or this. So how will it relate to the graph of that?
It would be inversed. So
So
it would
how
be,
does the graph of an inverse relate to?
wouldn't it be mirrored in the x-axis?
No, that would be going from any function to the negative of that function, which is a kind of inverse, you might say. True. But it's not the kind of inverse where we're swapping x and y.
Would it be in the y-axis?
And that's where you're going from any function to the same function of the negative value of x. So those are not the right reflection, but we are going to reflect. We want a reflection which captures the fact that we're swapping x and y. And that reflection will be in the mirror line, which is not affected by the reflection. That's right. We want the line y equals x, as you say, because we want all of those points not to be affected. Because y already equals x. They are their own reflection.
Yeah.
So yeah, we're going to go like that. Is y equals natural log of x. So not those.
Yeah, no, not them.
Those are kinds of inverse, sure. They're reflections, but they're not generally inverse in the strong sense of swapping x and y. So the graph of log x always looks like that, and it doesn't quite reach the y-axis.
When you're inversing a graph,
yeah,
are you always
always? Yes.
Are you always mirroring it in the y equals x?
Yes, exactly. Absolutely. Always.
So even if you had
the
like
inverse of a graph is a reflection in the line y equals x. Yes.
Okay. What exactly? Could you explain e to me again? Because
e to the x.
No, just e. What e means?
Oh, the number.
Yeah. Because I know it's like 2 point something, but what exactly does it's like the gradient of something, isn't it?
Well, what's special? Yeah, there's lots of nice special things about e to the x.
It's like 2.7.
But e itself, I'll have to.
What does it mean? What does e mean? Like, why is e the
why is
number?
it significant? It's significant because the derivative of e to the x is e to the x. So it is its own gradient. You look at every y value, and that'll be the gradient at that point. For example, this point will have a y value of what?
1.
Like anything to the power of x, it'll be 1 at the y-intercept, yes?
Yeah.
So in the case of e to the power of x, we know the gradient there will also be 1.
Yeah.
As the y values increase, so does the gradient. I mean, that's true for anything to the power of x. But with e to the x, you know the gradient is actually, yeah, sorry?
So the gradient increases with the y value.
Yeah, but that's true for that's true for 2 to the power of x. But for e to the power of x, not only is the gradient increasing as the y value increases, but the gradient is always equal to the y value.
The gradient is always equal to the y value. Right, okay.
I mean, for 2 to the x, you can see that the gradient is increasing all the time. But for e to the x, you know the gradient is always going to be exactly equal to the y value.
Right, okay. Even the negative ones?
Yes. Because here, for example,
Mm.
the gradient is positive, you're saying.
Yeah, and it's still positive in the y.
The
Yeah.
y value still is positive, only the x is negative. But yes, of course, your gradient here is less than 1, which indicates a negative power, doesn't it?
Yeah.
The power you have to raise some e2 to get something. In other words, the inverse of e to the x is going to be negative. At the, the inverse over here, reflecting in the line y equals x, this is going to be a negative y value.
Yeah.
So for I'm losing. I'm half, I'm not quite following what I'm saying here, but I'm sure it does make sense. That's good, isn't it? But I mean, it's so mind-bending. You've got e to the, say this was e to the minus 2.
Yeah.
So the y value here is the power you have to, is the result of raising e to the power of minus 2. Therefore, minus 2 down here, if we go to the inverse of that,
Yeah.
this would be minus 2, which is the power we have to raise e to get no, hang on.
So
Yes,
when you've
to
got,
get this value here, which is that y value there, which is what we get when we raise e to that power of minus 2. Sorry, you can be forgiven for not following that.
so is e only really relevant when you're using e to the x? Because so you say e to the x, so you've got the equation y equals e to the x, and then all the y values will equal the gradient at that point, but surely
Yeah,
that would only work
that's a good
for
point.
the equation e to the x.
That's a good point. I mean, pi is a number, and we very often look at the number itself
Mm.
and say, okay, we want double that. It's not so often that we look at e and say, okay, well, we want double that. What is it? We do get e as a result of certain solutions, as a solution to certain problems. Yeah. So we do. It is a constant. But if you're saying I shouldn't be worrying what it is as a decimal approximation, because it always, you only ever really meet e apart from if it turns out to be the solution to some problem. Really, you're always thinking about e to the power of something. Yes, it's the exponential function you're thinking of, really. Yes, it's basically a standard parameter for this kind of function called an exponential function, where x is the exponent.
So will you ever see e in the form where it's not something e to the x? See what I mean? Like, will you always see e with e to the x?
Well, this y value here is e to the minus 2.
Yeah, but would you ever get like 2e?
As rarely, no, more rarely, you never get 2 sine, do you? So it's not quite as extreme as sine, which is only ever sine of something. E is a constant, so you can have it on its own, but it's almost, the answer to your question is almost yes.
Right.
Yeah,
Okay.
E is almost always e to the power of something, yes. E to the power of a variable. Yes.
Good. Okay.
Yes. No, I absolutely see the point of your question.
Yeah.
The answer is roughly yes.
Mm.
Where were we? Yeah, so those are the kinds of questions they're hoping that you'll start to ask. Yes, to get to start thinking about the relationship between exponentials and logs. exponentials in general being not necessarily e, but some number to the power of x. And don't forget, e is e for exponential. It is the capital letter of exponential. And exponential, well, an exponent is just another word for a power.
Yeah.
Really, exponential means a power function. In other words, some constant to the power of the variable x again. So e just means a particularly valuable parameter to use to raise to that power. So it is talking about this kind of function, yes, e to the x. The very choice of e as a letter of the alphabet is pointing to the fact that its main use is this kind of function, raising that constant to this variable power.
Right. Okay. So in that last equation where we said y, what was it? Y equals ln x.
Here?
If you got so that's the inverse of e to the x. Right. Okay. Because we've got what we're raising e to get x. Okay.
I don't think, I was just looking at these and thinking, have I drawn that right? I don't think these meet the line at all, the mirror line. Yes, I think I've drawn it right.
Yeah.
I don't think it would be a waste of time to get this graph page again. Just ask it, oh, stop it. E to the power of x. And oh yes, look how far it deviates from the line y equals x. And then natural log of x. Yes, yes.
They're inversed.
Then you can see how I should have had these. Well, they were tending to, but I was worrying about that they should be diverging again. But yes, they definitely should diverge again. Look at them.
So when you've got okay.
Right. Yeah. No. Keep.
No, I don't, I don't even know what myself what I was about to say really. So when you've got so you could rewrite log x. How could you rewrite that?
Oh God! Look what I did. Maybe you're worried about that. Sorry about that. I didn't mean log to the power of x, did I? I meant log.
Well,
of
means, so what do you raise e to get x?
That's what this says. Yes.
So how would you rewrite that without the log? Could you
with
do
difficulty? That? That's why we need to have this potentially mind-bending symbol called log. It just means the power you have to raise e to get this value. For example, the power you have to raise 10 to get 100 is 2.
So say you had 10 to the x, would the inverse be, or 10's well,
yeah,
say
but for example, supposing you had 10 to the x equals 100, what would the solution be? X must be
2.
2. But that's exactly what this is saying. It's just referring to this solution to that equation.
So would the inverse of that be log 10 to the x, log 10x? I mean,
in general, the inverse of log 10x equals y would be x equals the power we have to raise 10 to
10 to the y.
Sorry, so that means that, and then if you swap x and y, you get that. So y equals 10 to the x. Sorry, that's what you're asking, and I was just too addled to say yes to your conjecture. Oh, hang on. Oh no, was that your conjecture that that 100 is 10 to the power of 2? Which of course it is.
Well, the inverse of 10x would be log 10 to the log 10x.
So the inverse of log of 10 to the x.
Is it log 10x? Log 10x.
Yes, log base 10 of x.
Yeah, log base 10.
Absolutely. X. Oh yes, and by the way, once you start to grasp that those are the inverse of each other.
Yeah.
That's why you can do balancing like this. Suppose you've got, and that will happen today probably in the forthcoming exercise. They'll say, I mean, if you've got something like 10 to the x equals, I don't know, 3x plus 2, then you could say, because these are inverses, I know that log to base 10 of that, damn, I wrote that wrong, on a level there. Log to base 10 of that would be log to base 10 of all that. Because I know that those cancel because they're the inverse of each other. And I'm just left with x equals that.
Log base 10 to 10x.
If the power you have to raise, if x is the power you have to raise 10 to get that,
Yeah.
well, this is just another way of saying that. X, you know, if the power you have to raise 10 to, if x is the power you have to raise 10 to get 3x plus 2.
Yeah.
Well, this is a way of saying that. X is the power you have to raise 10 to get that. That is how to read a log, the power you have to raise that to get that.
Yeah.
And then you could translate it like that.
Yeah.
Well, I'll jolly well raise 10 to that power then, to x, and put it equal to that. You can always convert that to that.
Yeah. Okay, I see now. Yep. Yep.
And when I hear, and I do, when I hear students adopting that form of words to themselves and muttering, all right, the power I have to raise that to get that, it's potentially mind-bending, as I keep saying, but it works for people, and they can get to the bottom of problems. Hopefully these kinds of problems that they've got in store for us. What was this about then? Recall, to do this one, part A, they said 2 to the minus x, think of it as 2 to the power of minus 1 of x. Yes. That's the kind of thing I was getting at down here with the e to the x is 5 to the minus 1 would mean that e to the minus x is 5 to the 1. It's kind of what they're getting at there. It's different as well. A bit different. Anyway, let's look at the next one. I think. Right. Or shall we? No, let's not be in a hurry. Let's do these. Okay. Express log to base a of that in terms of log to base a of that and that. So let's definitely translate this into the power you have to raise a to get that. Now, how can we do the translation? Because what we should do really, also, what you wouldn't, they're not expecting you to do that. They want you to use the various general rules, don't they? They want you to say, log to base anything of a, different letters, x, y, expands how? Can you recall?
Log x plus log y.
Yes. Now, every time you say that to yourself, you might be thinking, and why the hell is that? Something to do with powers?
Mm.
Yeah?
Yeah.
I'll fix that on another occasion. And that's what I'm doing now. I'm saying, look, I'll teach that on another occasion.
But those logs then, are you basically saying log base 10x plus log base 10y?
Sorry, say again?
You see those, so the way you've written it there, log x, log y.
Yeah.
Does that mean log base 10x?
Oh, it could do. It could be log base anything. Could be log base 5, e, 10. Doesn't matter. Doesn't matter what the base is.
Right.
Let's have a look. Okay, we've chosen 5 there, right? Let's have a look and try and make this work. The power you have to raise 5 to, what should we call this power? Not P and Q because they've used that. Not A and B. Let's just call it blank. The power you have to raise 5 to get x, y. How would that relate to the power you have to raise 5 to get x, and the power you have to raise 5 to get y?
It would be
Well, I mean, x, y in that case would be, sorry, yeah? 5 to the power of what? If this is x and this is y, tell you what. Draw that as a circle. So if x is 5 to the power of square, and y is 5 to the power of circle, xy would be 5 to the power of what?
xy would be...
I mean, it would be 5 to the power of square times 5 to the power of circle, wouldn't it?
Yeah.
Which would be 5 to the power of what?
Which would be 5 to the power of square plus circle.
It would, wouldn't it? Because you can think of simple examples, like if that was 2 and that was 3, you'd have 5 to the power of 5, wouldn't you?
Exactly, yeah.
Okay. Which is why the power you have to raise 5 to get essentially xy, this power that you have to raise 5 to get xy would be the sum of these two powers.
Yeah.
But this is the power you have to raise 5 to get xy, isn't it?
Yeah.
And that's the power you have to raise 5 to get x. And that's the power you have to raise 5 to get y.
Yeah.
And now you can see why that's true, can't you? The power you have to raise 5 to get xy is this power plus that power. That log plus that log.
Yeah, I can see that now, yeah.
Anyway, I'll leave it there. That came out all right. I mean, that's the kind of situation I'm dreading when I take the easy option and say, leave it for now.
Yeah.
It's mind-bending, but I think that'll work there.
Mm.
I think that's
Yeah.
an okay diagram. Right, I'll use that next time. And so, you know, if it's not working for now, and you're just being kind,
No,
and, and, and you're totally lost, but in which case you should tell me, and I'll accept
well,
that. We'll start
wouldn't
again.
you make the you see that first 5 equals xy?
5 to some
Wouldn't,
power or other equals xy, yes. So
wouldn't
this
you make
power
that,
here,
yeah, that square, like a square circle?
that square is, and I shouldn't do it as a square because that's a square. Oh,
Yeah, that's what I was saying. Shouldn't you make it a square circle, like a square and a circle or something?
oh yeah, yeah, it should be that plus that, like it is down here. Absolutely.
Yeah.
Yeah, because xy equals that. Yes, I'll make it a different shape because to leave the question open whether it's square or circle, if you pardon my, if this isn't sort of just getting carried away, but if we make that a diamond, how's that? 5 to the power of diamond is the power we have to raise 5 to get that. And it turns out that diamond equals square plus circle.
Okay.
Diamond equals square plus circle.
Yeah.
Right, so that's a rule. The power you have to raise, log of a product always, as you just told me, you did remember the mechanical rule. And so do be aware that you can check the meaning of it as well if it helps. So from that one, a particular example of that would be that log of 2x, hang on a minute, what am I saying? Log of x squared, which is xx, call it xx, why not, to make the point. Log of xx would be what?
Log of x would be log x plus log x.
In other words, yes, and log x plus log x, well, let's write it like that. In other words, log of x squared equals
2 log x.
2 log x. And notice it doesn't matter what the base is. It didn't matter that we used 5, we could have used anything.
Yeah.
And this is a case of that other mechanical rule we talked about, isn't it?
Yeah.
You can, if you've got log to something to a power, you can always bring the power around the front. Because I seem to remember we were differentiating log of x squared. And we noticed that we could just simplify it by differentiating 2 log x.
Yeah.
Okay.
Okay.
So, using those 2 principles, how do we expand log a of p squared plus q?
So that would be log a to the p squared, log base a p squared plus log base a q.
I'm glad you mentioned the base a, because it doesn't take that much. You know, people are too lazy with logs, and they don't make it clear what they mean. But you don't have to. It depends whether you want to mention the base, but it's just not that hard to do. You might as well just say.
It makes it confusing. So if they don't mention the base, so if you just see a log where it's actually written log,
then you can take it for granted they mean
10.
10. Yes.
And ln is always base e.
Yes.
Okay.
Yeah, because I think that the n there means natural.
Yeah, that needs to be like emphasized when this is taught, because otherwise you could get confused.
Absolutely.
Yeah.
Wow. Yeah. Maths is just all about things you probably have missed that were taken for granted. Yeah, that's maths,
Yeah.
isn't it? Yeah.
Yeah.
So, and but so have we expressed it in terms of log A of P and log base A of P and log base A of Q? Not quite. We've got
Okay,
log
and then,
base A of P squared, not log base A of P. So we could
then it would
rewrite
be
that.
2 log AP
Yeah. Plus the other one.
plus log base AQ.
Good. Now, given that, they've used 5, that's a complete coincidence. I hope that's not off-putting. So given that log base A of PQ is equal to 5, and that which we've just expanded is equal to 9, can you see how to attack problem B?
Find the values of log AP. Okay, well, you could probably do simultaneous equations or something.
Yes. And the second of the 2 simultaneous equations will be?
So you'll have log, wouldn't you just use the expanded forms of those 2?
Yes.
So you'd
Well, we've
have,
got this expanded form of that one.
yeah, and
And we should
log
put that equal to, by the way,
9.
9.
And then you'd have log log base AP plus log base AQ equals 5.
Good. In which case?
In which case log AP equals 4.
Yes, I would resist the temptation to drop the
So
base.
yeah,
Use
base
the word
AP
and of, probably. Log base A of P, it's a good habit, equals
equals 4.
4. In which case?
In which case log base A of Q equals 1.
Yeah. In which case, oh no, they just wanted the values of the logs.
Well, that would have been, what, 5 easy marks?
Yes.
That is really just a matter of like knowing. I mean, it's the same with everything, isn't it? But just if you knew how to do that, the simple rules, then that would be easy marks. If you didn't,
Yeah.
you just get
And
low
the thing
marks.
is, the rules do become simple. You know, you've got this underlying brain bending logic, but
Yeah.
then you just get used to using the rules correctly. As long as you can go back and examine the logic, you just rely on mechanical rules. And then it's only the mechanical rules that get taught and anyway, with practice, it's all fine. But make P the subject here. Bonus point.
P equals A to the 4.
Yes. Because the power we have to raise A to get P is 4.
And Q equals A to the 1.
So just A.
So just A.
Yeah. And that, of course, it is a kind of result from, is it from this? Or is it just from the form of words, really? You know, it's just a kind of result, be aware of. Special results are log to the base anything of that base equals
Equals A to the power 1.
which is why Q did equal A, because a 1 there means that these are the same thing.
Yeah.
And log to base anything of 1 is
0.
because the power we have to raise anything to get 1 is
0.
yes. So just sort of special log facts. that you will find cropping up. I need to turn a light on here. Right. Yeah, why don't I do that? Hang on a sec. Okay. Okay, given that P equals log to base Q of 16, what's log to base Q of 2 in terms of P? Yes, this, how could we attack that?
Okay, P, so what do you
So we know that
use?
P equals log base Q of 16. Well, how could we rewrite that?
We could say Q to the power of P equals 16.
Oh, that's true. Okay, that would be one way of Q to the power of P is what equals 16, yes.
And then, so we could say Q to the power
Yes.
Of something P is going to equal 2. And it will
Yeah.
most likely be...
Well, hang on now. P times something, because what you're doing is saying, let's raise each side to the power of something. And that power here needs to be this power here, such that that's equal to 2.
Yeah. Well, 16...
We're doing this. We're doing this a complicated way. Bear in mind. So don't panic if you think.
No, this,
worse.
yeah.
But you know, logs are invented to make this simpler. But it's good to see the logic here.
Okay. Well,
so
16
what's this power?
Quarter.
Yes. Because 2 to the power of 4 equals 16.
Yeah.
Right. So, in other words, Q to the power of a quarter P equals 2. Is that what you're thinking? Sorry, I shouldn't take over there.
Yeah, I was originally going to say like a quarter root. I don't know, a 4 root. I don't know what you call that.
Well, raising to the power of a quarter is taking the 4th root, yes.
Yeah.
But it wouldn't be the 4th. I mean, you could rewrite. You could write it like this: Q to the power of P all to the 4th root. That is true.
Right. Okay.
Not very helpful, I don't think. But now we can give the answer that that's equal to what?
That's equal to a quarter P.
Yes, because the power we have to raise Q to get 2 is apparently a quarter P.
Yeah.
That form of words really does help.
Yeah.
Even though it can be mind-bending if you're getting sometimes, but other times not. This just makes sense of it, doesn't it? Power you have to raise that to get that, fine. And what about what would this be in terms of P? Gosh. So this was about expressing 16 as a power of 2, essentially, wasn't it?
Yeah.
And you found the right power of 2. It was 2 to the power of 4 that we had here.
Yeah.
Yeah, actually, let me show you the quicker way of doing that. It would have been P equals log to base Q of 16, which equals log to base Q of 2 to the power of 4. And what was the rule? We're just allowed to bring that round there.
Yeah. Yeah. Okay. But oh,
Right. So you had 4. And you're saying but for the same reason I was saying but mentally.
it's multiplying.
It's multiplying. But that's p. And therefore, but it does turn out then, doesn't it, that log base q of 2 equals p. Yeah, a quarter p. So we do get to the same place.
Hold on, I'm a bit baffled. So P equals 4 log Q.
Because that was equal to p, you see. If p is log to base q of 16, then p is log to base q of 4th power of 2, because 16 just is 4th power of 2.
Yeah.
Now, using the mechanical rule from the example you showed me somewhere. No? Where was it we discussed that? Oh, way over here. Using this mechanical rule, because log of x squared must be log x plus log x, which is 2 log x. In general, we can see the effect of that is that we can bring this power around to the front.
Okay.
And that's what that would be the easier way of doing this. What we did here was clever. It's good because we're using that form of words from the word go and then using it again later. Here, we're not bothering with the form of words. We're just saying 16 is 2 to the power of 4. Bring the 4 around the front. So P is 4 log base Q of 2.
But how is that to do with 8Q?
Oh, no, quite. Well, because just as there was a more mechanical way of doing of A than we did the clever way, I'm going to suggest with 8Q, we start using the mechanical way and just say, look, if we want to compare this to this, can we somehow express 8Q as a power of 2, like we did here?
Okay, so 2 to the power of 3.
And
Q.
then we'll get back to P from there. Yes. I mean, so starting, just rewriting, log to base Q of 8Q. You're right that that's 2 to the power of 3. Shall we actually shall we take these apart? We've got a product, so shall we split it into 2?
Yeah.
So writing what?
I'm a bit confused. How would...
Remember the rule that we were discussing here? Log of a product equals the sum of 2 logs.
Yeah, of course.
That reason now.
Okay, so log Q of 8 plus log Q base Q of Q.
Yeah, excuse me for writing. Yeah, why am I writing it that way now? Of 8 plus log base Q of Q.
Yeah.
Which equals, working with that?
Which equals... Where that equals log base Q of 8 plus 1.
Yeah, but 8 can be written as
2 to the 3.
2 cubed.
Yep.
And log base Q of Q is
1.
1. And we can rewrite that again.
3 log base Q to the 2.
Yeah.
plus 1.
Good. Now, what's that in terms of p they want to know? Well, we can
P,
use part A, can't we?
yeah.
We can say, what's...
Yeah. 3 times a quarter p plus 1.
Yes. Yeah, yes, that's right. I was overcomplicating it there. We can just replace that with, because they do want it in terms of p, not log 2. So replace that with a quarter p, yes, which equals finally what you said, but simplest of all,
3/4.
3/4 p, yeah. 3/4 p plus 1. Splendid.
Yes.
Right. You see, they're getting easier. And, but you've got this book, haven't you?
Yeah.
Good.
What section is this?
End of book 1.
The end of book 1. Okay.
Yeah. Solve these equations, giving your answers to 3 significant figures. So apparently the power we have to raise 4 to, or x is the power we have to raise 4 to get 23. So we would say next what?
Log base 4 to the 23.
X equals, yes, power we have to raise x to, sorry, have to raise 4 to get 23. Plug it in the calculator, whatever it is. B?
Do you want me to put it in a calculator?
No.
No.
Not worth it, is it?
Oh, B. I thought you. Okay. I didn't
Yeah.
what you said.
It would, no. I mean part B. Yep.
Yeah. So log base 7 to the 1,000.
Right. Or I would rather you were. Oh no. All right. Because what you're saying is log to base 7 of 7 to the. What I was trying to show you earlier and failed was that you could, if you take logs of both sides, which is what a lot of people say, take logs of both sides. Look what's happening, and that cancels that. And you're just left with that equals all of that. But then that's what you were about to say anyway. You were saying,
So wait, what are you left with on the left-hand side then?
just that. It's like the log to base 7 is cancelled with the 7 to the power of.
Yeah, I was about to say that. Yeah.
Yeah, because, but after all, the form of words was going to tell us that anyway. If we just look at that and say the power we have to raise 7 to get that is that. So that is, we could say that is, that power is the power we have to raise 7 to get 1,000.
Yeah.
And then just make x the subject, which would be what?
Log base 7 to the 1,000 minus 1 over 2.
Yeah. And then, yeah, let's try using the form of words. Oh, no. I don't know.
Yeah.
Well, yeah.
Well,
Let's use the form of words.
So
x is apparently
x is log 10 to the 6.
You see how the words are getting garbled.
Well, then we just times it by x plus 2, wouldn't we? We'd say x plus 2 at the front. So it'd say log base.
Yeah, can I just pick you up on, when you say to the, if you don't say base, then you're going to say to the something wrong.
Oh.
So what you do mean is x is the power we have to raise 10 to get this result. and you were beginning to put it this way. You were saying x equals log, and then you said 10 to the, but you meant log to base 10 of
log to base 10 of 6
6
x to the x plus 2.
to that power. And now we would be very well advised to do what you're saying, which was this thing you were trying to tell me, weren't you?
Yeah, take the x plus 2 to there.
So it equals x plus 2. And then what?
Log base 10 to the 6.
Of 6. Try to say of instead of to the.
Sorry, log
Because
base
to the
6.
suggests a power, doesn't it?
Yeah.
Of that. I mean, it's all about powers, I know, but gosh. And then?
And then you could
Forgetting about this bit and just saying x equals that, and we're trying to make x the subject. So
I don't know, would you say x over x plus 2 equals log
absolutely,
base 10?
that's correct.
Shit.
Now, your only difficulty now is log to base 10 of 6. Well, that's going to be a decimal approximation. That's fine. You leave that for the calculator. But before we do that, we can make x the subject, or can we? Because we've got 2 mentions of x here. And how the hell do we deal with that then? And, you know, it's a tough one. But it's got a very easy answer, which is take the reciprocal of each side. Happy with that? Oh, have I lost you?
Yeah, no. How did you
Oh,
get
no.
x plus
Oh, good.
2 over
Sorry.
2? How is it over 2?
Because I'm an idiot. Thank you for drawing that to my attention.
That's confused.
What? What? Why is this not working? Go back a bit. Oh no. Oh, text. Escape. Rectangle. No. Let's go back. Now. No. Ah! What's happened? What if I change? Wonder if it's about that. No. What else happened? We had text. Oh yeah, I was gonna say. Mm, I mean, what about? Um, oh, right. Sorry about that.
Mhm.
Where are we? God, how did I change black to white? Right. So that equals x plus, or rather, if we take the reciprocal of each side, we do indeed get x plus 2 over x, is what I meant, equals 1 over. Okay, you see what I meant by taking the reciprocal of each side?
Yeah, I see what you've done. Yeah, but I
Now,
don't know how.
what's the advantage of doing that? The trouble is, this, we're stuck. We can't split the fraction. You can't split a denominator, but you can split a
Um,
numerator,
yes, of course. So now you've got x over x plus
which
x
is
over 2, which is 1 plus 2 over x.
2 over x. Ooh, this is horrid. So therefore,
Therefore, 1 over log 10, log of base 10,
log base 10
6,
of, you mean?
log base 10,
It's
log of
worth,
base,
it's worth being
log,
fastidious
yeah,
about that.
log base 10 of 6 equals, equals,
Well, I mean, you
it
could
will,
say 1 over, so far you've said this, but that would just be that, wouldn't it?
yeah, I mean, well, it would be 2 over
Yes,
base
yes.
10,
Let's, we could say, therefore, 2 over x equals,
1 over log base 10 of 6 minus 1.
good. And given that now we want to take the reciprocal again, it's going to be a very messy reciprocal if we have that. So we're better off not doing that, but having another form of this would be, let's turn this into one fraction. How could we do that?
Uh, 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 1, you could just put that minus 1 at the bottom.
Oh, wouldn't that be nice if that was possible? Can you ever do that? Can you say
Or,
a over b minus 1 equals a over b minus 1? Nah.
maybe
What you
not.
have to do is you have to say, look at it as a over b minus b over b, don't you? Equal, because then you could say
Yeah.
a minus b all over b. Let's do that here.
So 1 minus 1 over log 10.
1 minus 1.
1.
If we follow this format, we've got to turn the 1 into,
Minus 1 over 1.
is that what we're doing here? We're turning 1 into b over b.
Oh, so log base 10 to the 6, not to
Of
the
6.
6, to the 6 over 2 log base 10 of 6. Yeah.
And then
Okay.
finally x equals, or x over 2 equals
X
the
over 2
reciprocal of that.
equals, yeah, the reciprocal of that.
And therefore x equals,
Therefore, x equals All of that times 2.
Which we can put the 2 on the top there as well. And then that on the bottom. If I haven't made a mistake somewhere along the way, that was pretty complicated, that one. Well, that's probably how they designed it. Right, okay, good.
Mm-hmm.
So there you are. Yes, I will send all of these over.
Good.
Probably full of mistakes. Anyway, good. Yes, I'll do that. Good. Yes.
Good. All right then.
Okay,
Cheers,
cheers
Tom.
then.